Hello. In this ACE session, Assistance with Chemistry Examples, I want to go over two classic synthesis problems using alkyne chemistry. For these two problems, I will be looking at my reaction roadmap for alkynes, and here in the center of the roadmap we have an alkyne, and I'm performing several different reactions, but also I can show how to make an alkyne starting from an alkane going through the alkene. And it looks like we'll be doing that for the first problem. Let's talk about strategy. The first thing is you want to notice, do you make any carbon-carbon bonds, or did you add any carbon to the starting material? And it looks like we do. And let's see, if I can maybe try to mark this carbon right here. Okay. 1, 2, 3, 4. 1, 2, 3, 4. It looks like it's this carbon, and we had to have made a carbon-carbon bond to get this carbon at the end. So this is a key carbon-carbon bond we're making. In total, this is C 1, 2, 3, 4, 5, 6, and this is 1, 2, 3, 4, 5, 6, 7. Okay. Not only do we know that we have to add a carbon, we also started with an alkane and ended up with an alkyne. There's only one reaction we can do with an alkane right now, and that's the radical halogenation. We went over this in the radical unit. What else should we say? Oh, how to make this carbon-carbon bond. In the alkyne unit, there's one main way. You could have an alkyne, terminal alkyne that's been deprotonated, plus some type of alkyl halide. And that's how we could do an alkylation. Okay, why don't we get started? I think we all know what the first reaction should be. This one right here. Oh, it's the same actually. It's the same starting material. Okay. Anyway, this is for problem A. Now, when I look at my students' exams, many times I could tell that they know the strategy or they know approximately what to do. It's the formatting that kind of gets them in trouble. So you want to be as neat as possible and show a reaction, the product, the major product if there's a mixture, most likely, and then the next reaction in a very organized fashion. And here we have bromination on the secondary carbon. The next step is to make the alkene through an elimination. And let's see, I like to use NaOET as the strong base. And actually, there's only one beta carbon that has a hydrogen, and it's the one on the right. That's the alpha. And we have two beta carbons, one on the left, one on the right. But we can't make the double bond to the left because there are no beta hydrogens. We'll make the beta, we'll remove the beta hydrogen on the right to make the alkene. Now there is no direct way to go to the alkyne from the alkene. We have to go to this city, the dihalide, and that is first Br2, CHCl3 as the solvent, and I have this. Okay, now, so far, really all we've been doing is copying this roadmap. Okay, and in this last reaction to the alkyne, we have three equivalents of NaNH2, and then we protonate the carbon anion. The thing is, if we really want to do an alkylation, why do we protonate it if we're going to have to deprotonate it anyway for the alkylation? So here's the shortcut. I'm not going to protonate in this step. I'm going to leave it as an alkyne anion, and You know how I talked about formatting? Well, I don't want to draw the alkyne. I want to draw the alkyne anion. I'm still going to use 3 equivalents of NaNH2, but I'm not going to protonate the terminal alkyne. I want to keep it deprotonated. And that gives me this. So instead of drawing this neutral, I want to keep it as the anion because I want to keep it as a good nucleophile. And what electrophile do I want to attack with this nucleophile? I want to attack an alkyl halide that gives me that CH3 group at the end. So that dot actually is the attacker, and this is the attackee. I'll show you that. This is a methyl halide. What's going to happen is that the carbon anion, when it's a triple bond, the general name is acetylide anion, attacks this carbon, kicks out bromine, and is that it? That might be it. We have our final target. Just double check that you have the right number of carbons, 1, 2, 3, 4, 5, 6, 7, and I guess that's it. So I call this one of the classic synthesis problems for alkyne chemistry because it takes you from an alkane all the way to an alkyne, but also we add in, or in this synthesis, there's an alkylation step. This one's an alkylation. And there was no reason to protonate this, the alkyne, since we needed deprotonated to do the alkylation. And one last time, classic synthesis, alkane to alkene to alkyne. How about problem B? Problem B is another classic synthesis because we have an alkene to an alkene. So what changed here? The stereochemistry changed because here we have a trans alkene and the final target is a cis alkene. Now they look very similar, but a lot of times when you have very similar products to reactants, you have to go through an intermediate product that may not look as similar. That's one of the counterintuitive things with synthesis, that you could seem very, very close, but sometimes you have to go take a detour to get to the city that you want. And same thing here. We have 2 alkenes, right? But we have to actually go through the alkyne to get to this alkene. Why? Because the alkyne, when it's an internal alkyne, gives us an opportunity to choose whether we want to make the trans alkene or the cis alkene. Okay. There is no reaction that's typically taught in organic chemistry where you could just convert a trans into a cis in one reaction. You have to do several steps. So in this case, the note that I want to make is that we want to go through the alkyne, or we could also say that we can make an alkyne go to a cis alkene using what? So the last reaction most likely is going to be the one with H2 and Lindlar's catalyst to make the cis alkene. So that's our end game, our last reaction. Now with synthesis, you want to try to get as much points as possible. So let's say, I don't know, let's say we forgot how to make an alkene through elimination. Well, just draw your road, even if you don't know the name of the road. Okay, at least you'll get credit for continuing the path. All right, and I only mention that because maybe the only thing you do know, under test conditions is that the last reaction is this. Then write this and don't worry about, well, at least you'll get partial credit for that last reaction. But I think we can we have a way to make an alkyne from an alkene, and that is through the dihalide again. Again, it's the formatting and it's how clear your structures are, and making sure that you have the right number of carbons. So I put 2 dots there between the uh, carbons of the double bond, and I have that dot. I made the dibromide. Okay, good. And I have one last carbon there. Oh, actually, I copied that wrong. There are 2 carbons after the double bond carbon. That, up like that, and right there. Okay, here we're going to use NaNH2. I don't take off points if they don't put equivalents, if my students don't put equivalents, but technically we need 2 equivalents, or you could say excess. NaNH2 to do a double elimination. Why are we trying to get the alkyne again? Because from the alkyne we can make the cis-alkene. And then don't forget that the cis-alkene is made with H2 and Linder's catalyst. Linder's catalyst actually is a weakened form of palladium, so you don't go all the way to the alkane. And I think that's it. H2. Most professors will let you just name Linder's catalyst. You don't have to write the chemical, but the chemical is palladium with calcium carbonate. All right, draw the product. Oh, here's another trick. When you're drawing an alkene and you're worried about cis and trans, or you want to specify cis and trans, why don't you just draw the double bond first, horizontally, and then we want it cis, so make those 2 groups on the same side. And that's clearly cis right there. Let's see. Maybe, let me try to find another synthesis for us to do. We do have some time. Okay, I found a challenge for part C. I think this is a challenge because we have several functional group changes that aren't apparently, or at least initially, linked together. For instance, we got to get rid of 2 bromines, and we have to figure out a way to get an oxygen onto the molecule. The good news is that both of these molecules have 4 carbons. So I don't think we're forming any carbon-carbon bonds or breaking any carbon-carbon bonds. Now, we could either work through this forwards or backwards. We do have, what I would suggest is give the class of molecules. We have a dihalide, and with a dihalide, we could make an alkyne. Okay, we could make an alkyne. Now, would that serve any purpose? We're not doing an alkylation. We're not adding bromine, I don't think, to make the final product. But we do have these 2 molecules here, an aldehyde and a ketone. So we are doing, in both these cases, a type of hydration because we're adding oxygen and 2 hydrogens. So here we have a ketone. And we have to be able to recall that we can make a ketone from a alkyne. So probably the last reaction is an alkyne to a ketone, one of the more trickier reactions to remember. And we have a way to go forward because we could form an alkyne from a dihalide. This is my synthesis. Oh, in this case, we do want to have the neutral alkyne. In the previous case, remember how, or not the previous case, but in the first example, we wanted to keep the anion because we want to do an alkylation. So we're right here, actually, right? And here I kept the anion, but in this case I want to have the neutral alkyne because I want to use that neutral alkyne to make the ketone. It is going to be a terminal alkyne, so this is a case where you use 3 equivalents of NaNH2 and then protonate the alkyne anion. And we get this. Those are your 4 carbons. Okay. And then it's only one more reaction. So the synthesis is short, but visualizing how these functional groups are being lost and how they're being gained can be a little bit tricky. Now this reaction is putting the oxygen on the more substituted carbon. That is Markovnikov hydration to make the ketone from a terminal alkyne. We're using H2O, H2SO4, and HgSO4. And you've seen this before with alkene chemistry, especially the H2O under acidic conditions. And for alkynes, we also add HgSO4 to emphasize or to make sure that it is regioselective. So the oxygen goes on the more substituted carbon. And there's your ketone. Okay, I'm not going to go over the details of these reactions. You'll look through your lecture notes for that. But again, we're doing a hydration because, see, this carbon has 1 hydrogen. Now it has 3. So we added 2 hydrogens and 1 oxygen. So we did add H2O. I have time to do one more example. And it's this one right here. I'm going to use the same dihalide. And I'm going to make another carbonyl containing molecule, but it's going to look like, it looks kind of strange because we are missing a carbon. We're missing a carbon. Let me show you how to do this example. I consider this also another classic example. We've seen an example in this video to make a carbon-carbon bond, but now it looks like we have to break a carbon-carbon bond. This is C3, this is C4. Okay, let's practice our alkyne formation. You'll see why I want to do this. To break a carbon-carbon bond, I am going to use ozonolysis, an alkene reaction, because I know I could break a carbon-carbon double bond to get a carbonyl group, but we don't have a double bond. But there is no easy way to make this into a double bond without going through the alkyne, because here I'm going to use another reducing agent. You could use H2 and Lindor's catalyst, but just for practice, I'm going to use sodium metal and liquid ammonia. This is called sodium metal liquid ammonia reduction, but you could have used Lindor's catalyst as well, and I have this. So do you see where I'm about to go? I'm going to do ozonolysis. O3, oh, it's a 1-2 step. And then the second reaction typically is dimethyl sulfide. So yes, you do have to remember some old reactions. Organic chemistry is pretty cumulative. It builds upon itself. But here, remember with ozonolysis, you cut in between the 2 carbons of the double bond. So the reason why I wanted to show this is that we go through an alkyne, so it is part of the alkyne unit, but here we break a carbon-carbon bond. Classic, you're going to use most likely ozonolysis. And just as a reminder, in the first example, we made a carbon-carbon bond by alkylating an alkyne anion.